Today is my great pleasure to introduce our speaker, Larysa Baraban. She is leader at Hightech Centrum in Dresden. She recently started to build her new group there. So originally, Larysa graduated from National University in Kyiv. Then she moved to Germany at the University of Constance, where she did her PhD studies in soft matter and colloidal particles manipulations in the Professor Paul Leiterer. Then she made several postdocs in Paris and then returned to Dresden, where she's working now as independent group leader. So today she will speak about active particles and her recent results on active particles in crowded environment. And before I hand the microphone to Larysa, I would like to announce that this seminar will be recorded. So please mute your microphones and disconnect video. So Larysa, please.
Mykola, thank you very much for introducing me. Also, thank you for inviting me. And I try to summarize our recent research in a way that it's also clear to everyone. Here, as you can see, the title of my talk. Can you, by the way, can you see my mouse? The moving or not?
Yes, we can see the mouse.
Okay, good. So if you look at the title, the main focus is given to our recent result that is dedicated to light-driven silver chloride-based Janus particles. And here I wanted to make even like to extend the term that also were given by Mykola. It's not only by passive not interaction in a crowd, not only crowd environment, but also just in general, the microenvironment. The microenvironment in a way it's a little bit more complex, because here we can also try to speak about interaction with the wall, interaction with the like complex patterns, let's say, and of course also the passive matrix that makes that brings to the crowded environment. And I just wanted to see how I press it. I just wanted to bring us back to here just for a second to a sunny Dresden. The photo was done in June 2017, before pandemics. Now this would be, of course, all forbidden. And this is the time of the year when all ships at the Dresden, so there is like swimming of the multiple ships one day. It's like Elbhangfest called, and the people are meeting at the Elbe sites, and they also celebrate. So now we can only dream about such situation and such getting together, but I hope we also can be back to that, and we also hope that you can come to Dresden once, because apart from the fact that Dresden is a very nice city, it's also a city, I would say, the high-tech, which combines also very high concentration on the scientists per thousand of normal citizens, having the big university, Max Planck institutes, the Leibniz, Helmholtz, Fraunhofer, and so on. So going next to this, I just want to make very short introduction. This is one, I have in this presentation two of my favorite slides that I always show if I speak about swimmers. One of them is like a big global motivation that coming still from Richard Feynman about prediction, the artificial nanoscale tools that could help to manipulate single atoms, molecules, and some larger biochemical species. And the good thing here is that this visionary talk of Richard Feynman initiated probably or was the origin for the further development of the molecular electronics, of the nanotechnologies, and so on. But if you come back really to the manipulation of a species, one of the very interesting thing would be, of course, the development of biological and synthetic molecular motors. That you know that a couple of years ago, this topic got the Nobel Prize in Chemistry by Ben Feringa, for instance. And apart from the molecular motors, we can also speak about the tools, nano and micro tools that can manipulate the cells or even the tissue, transport it there and back, and to perform a lot of useful tasks. And micro and nano scale. So if you think about really a summary of a different existing artificial motors or tools that can do such useful tasks, we can name several groups, multiple groups of the motors that are driven either by means of the catalytic reaction, a chemical reaction, or they are driven, for instance, by a generating of a temperature gradient around the particles here that leads to the motion towards the colder side, let's say. Or there is an actuation of a motion, basically by means of a magnetic field, basically generation of the mechanical motion here, and in this case as well, where you have some spiral motors, or for instance, by the ultrasound driven. But there is always something in common in this system is that, okay, there are diverse mechanisms of motion that are mostly based on the formation of a chemical or physical parameters gradients that are, for example, due to the external field, induced torque and something like this. But the motion is generated and can be represented as, for instance, a theoretic slip that should be proportional to the gradient formed around particles. So in this case, the asymmetry of such objects is always very important and plays a crucial role. Apart from, so before we speak about more or less about the mechanism, but if we know already what is a mechanism of motion, we can also think what can be done with such objects. And this brings us more to the practical applications. And the very big group of researchers now in the world tries to move the application of the micromotors to the, for example, in vivo applications, where, for example, the motor can attach some microbe or some cell, transport it, for example. So there is here shown, for instance, the selective upload of some of a micro or a bacterium, but not the yeast cells, because there is a mixture here. But apart from the in vivo application, there are also big group of researchers that look in a different direction and say, okay, why should we go in vivo? Let's stay in vitro and try to do some useful mechanical tools at the micro scale in frames of lab-on-chip systems and so-called bioMEMS systems, microelectromechanical systems. And in this respect, there are a lot of developments going on, for instance, on the particle as a micromixers, for instance, or the particles can help to done by means of a 3D printing, for instance, can also transport the cells to specific incubation points. So, or for instance, the using of the phenomena that is used for the motion of the particles, but for generation of for motion as for making of the micropamps here at the micro scale. I hope it can be very quickly shown. So generally, one can also move in the direction of performing of some mechanical tasks at the lab-on-chip platforms. And let me just, something is going. And here our main task and our main goal also is that we are applying the spherical Janus particle swimmers and try to explore their interactions with, so to understand the mechanism of their motion and to explore their interaction with the environment. That could be the wall, substrates, patterns, potentials, and the other particles that could help us with this understanding to bring us closer to something like a lab-on-chip application. So I show here very briefly the small introduction to Janus colloidal particles. This I also do at the lectures. Maybe it's boring, but I try to be consistent. I like to be consistent. Is what do we know about Janus particles? Janus particles is the bits, or not always bits, with at least two physically or chemically distinct surfaces. So the normal ways of fabrication could be either emulsification or could be the synthesis of the particles with the mixing of the two phases here. Then another very common way of fabrication is also using of a metal deposition. It's actually a physical deposition of the metals at the surface and so on. The Janus particles are known already for a long time, first due to some fundamental interest, because they are frequently were used for the modeling of the condensed matter phenomena, like crystallization, for instance, and so on. And on the other hand, there are also a lot of practical applications, as we can see now, is that the people use it for the stabilizing of the emulsions, for instance, for the catalysis and so on. Here at this slide, I would like also to summarize very briefly what is our work, how we came to, to the point where we are now. And this brings me to one very, very short snapshots how we started to work when I was just finishing my PhD thesis. Is we were starting with the Janus particles as a system for modeling the condensed matter phenomenon, namely to understand how the assembly and orientation of the magnetic moments is happening in the frustrated antiferromagnets, for instance. And for this, we used the Janus colloidal particles with a specifically fabricated magnetic film with a cobalt platinum multilayers that have a perpendicular anisotropy, and in such a way generating a net out-of-plane magnetic moment for the particle. And then when we try to assemble them together with the help, for example, of laser tweezers, we see that the magnetic moments of such particles tend to orient all mostly within the 2D, and they are forming a specific structure that is specular for the so-called triangular antiferromagnet, forming the kind of vortices here with vortices here, and having the very specific stable phases which are needed, for example, to form, for example, using the 12 particles. There is also 27 particle consisting cluster and so on. So with the help of a modeling, we also came to the conclusion that we could try to consider the presence of not only dipolar moment here within the cap structure, but maybe also we could try to implement the multipolar expansion and to think that potentially there might be a contribution for the quadrupole moments here, because this fact helps us to the parameter S here in this model also shows us that there is a presence of the multiple of the quadrupole moment in this case. So we were starting from that, but then this was 2008, 2009, exactly the point where all the micromotors field were starting, especially also in Germany. And we found out that if you place such particles covered by platinum into the solution of a hydrogen peroxide, actually this is only the video that will not work. This is what I found out too late. The particles start to move, they still move chaotically, but the period where they can perform the deterministic motion is really extended. That leads them to kind of an active diffusion where their diffusion coefficient is no more corresponding to their sizes more or less, but rather to proportion somehow to the concentration of the fuel, hydrogen peroxide in solution. This was an interesting phenomenon for us, and we were also investigated it, and there were a lot of interesting works. It's in a collaboration already with Samuel Sanchez, with Oliver Schmidt, and also with a group at Stuttgart where Mikola was also working there before. This is, I think, our common paper here, where we're studying first of all, trying to represent the velocity of the Janus particles and of such hydrogen peroxide-driven Janus particles, and we were investigating the loading capability of such beads for the delivery of the objects. Yeah, and Mikola, I think, was working here on representing also the velocity as the phoretic slip. Yeah, and proportional to the gradient of a solid, which was in this case, I think, the oxygen. But by now the motion was rather chaotic, was not deterministic. So this is why adding the magnetic layer, the same magnetic layer that we had before, helped us to orient the motion along the magnetic field lines and to get the motion more deterministic. The next step, of course, is if you try to integrate into a microfluidic channels, what will happen? This will help us, of course, to plan some lab-on-chip experiments, some bioassays experiments, some loading and transportation transportation of the cargo, which was also done here by using, for example, the magnetic cargo, where the interaction between the motor and the cargo was magnetostatic and could be modulated by the orientation of the external applied magnetic field. So here the video is that you can see that the Janus particle can come specifically to the cargo shown like as a large particle, and then after uploading, it can transport it selectively, having the attractive interaction between the cargo and the motor. And then at a certain point, due to the repulsive interaction between them, it can simply release it at the moment where it's needed. And then, of course, also at the early stage, we understood that using the hydrogen peroxide maybe is not the most optimal strategy for the for doing the even in vitro experiment. We were also thinking in development of fuel-free systems where we develop a new magnetic layers that could be heated thanks to the magnetic hysteresis losses. This was one of the works, was very interesting. And then later on, we wanted to explore another mechanism, another stimuli, something like a light, where we use the photochemically active particles to study their motion, also to study their interaction with another passive players in the system. And because this system is represented by these electrokinetic motors, this was extremely interesting also to study the system in when we have really crowded environments, as also Nicola mentioned at the beginning. And if you also have a combination of this so-called dissimilar species, where we have a combination of passive and active beads, this was very much similar as this predator-prey system, you know, as it's shown also here. So this is like a short summary about what have been done, like very much as a summary. And now I would like to just say that now we're focusing on the interaction of the light-driven system with the environment, as it really can be important for multiple application as a sensor, for example, or some synthetic tool for lab-on-chip systems. So this brings us to the outline, and then we go very quickly one by one. So the main goal is to find out settings for using the Janus swimmers in the context of a lab-on-chip application. And for this we need, of course, to explore different aspects. It's like interaction of swimmers with the walls, also with a complex pattern potential, let's say like this, and finally also with a passive matrix. So for this we need to address multiple aspects. Is that we need to fabricate the particles with specific properties. And here we select the particles with the electrical charges. We synthesize both the positively charged and negatively charged Janus bits. Then we study the motion of such particles at the differently charged walls, substrates basically, motion of the pattern. And then finally, what else can happen if you study them in the microfluidic chips is that there can be also another players in the system, cells, microbes, other colloids. So this is why we also focus on that. So we try to address different aspects of the particles microenvironment. And we start in this case with the walls, I suggest. So these are pretty new results. One of the work is already almost published, another one is in the preparation. So this is the second slide that I like very much, that I like still from my PhD thesis. It's about the fabrication of a Janus particle. This is pretty standard work, and you see some first works are reported in 2005, but even before there are works of Micheletto, who was shown the first time the fabrication of such bits. So this is done by drop casting method and the fabrication of a self-assembled array of, in this case, polystyrene particles with diameter around 2 micrometers. And then we deposit in the metal films to form the metallic cap on it. So in this case, we are using a chromium 5 nanometers and a silver 50 nanometers. After deposition, the film is pretty flat. Please note it, because this will not be the case in the following. And if you observe them under the optical microscope, we see a pretty good optical contrast between the cap and the transparent side. As I promised, we want to fabricate the negatively charged particles and the positively charged particles. I would now start with the negatively charged bits, and they are fabricated in the following: that after the deposition and the dispersion of the particle in the aqueous environment, we place them in a solution of iron trichloride and the polyvinyl pyrrolidone. There is a mixture for 20 minutes. So this chemical reaction helps to get the kind of oxidize the silver, if you like, and to form a silver chloride compound here. Please note that generally not all silver is converted typically to a silver chloride. There is a combination of a silver cluster and silver chloride there. After this process, we see that the surface of a particle of a cap is looking really nanoparticulate, it's no more flat as before, and has a thickness of between 200 and 300 nanometers. The particles are getting a bit thicker. Such beads, because of the presence of both silver and silver chloride, can be now active in the blue light, in the visible spectrum. Please note that silver chloride generally is a photocatalyst for UV light. Look at this band gap here as a 3 and 2 electron volt. But the presence of a silver so in illumination of the blue light excites the excites the plasmonic excitation, excites the hot electrons that are transferred further into to the silver chloride, and then the reaction of the decomposition can start, and at the end it may help and contribute to the motion of the object. So after fabrication, particles are dispersed in aqueous solution, and by shining blue light we get the decomposition of silver chloride. Yeah, and we see that there is a motion under the blue light. Yeah, so the composition of a silver chloride in this case is so that there is a formation of a reduction of a silver, and there is formation of a protons and chlorine ions that, interestingly, but it's the fact that they have a different diffusion coefficients, and this is why they can form separate two clouds near the cap that forms the electric field that pointing towards the cap structure, towards the cap surface. At the end, what we observe that such negatively driven particles, negative Janus particle, that they have a zeta potential around minus 20 millivolts, sorry, and their motion at the glass substrate is observed away from the cap. This is important to remember because if we I think maybe I just noticed it very quickly, is that when we also do the quantitative analysis of such motion of, here in this case, there are 20 Janus micromotors, we see that they all move pretty consistently. The average particle velocity is around 6 micrometer, and MSD shows traditional parabolic behavior. I will not show anymore the slides for such a characterization of the motors because it's pretty standard, and all our motors, if they move, if they behave as the motors, they reveal similar behavior. But so as I told you that the negatively charged particles, they move away from the cap. Now I want to show also how do you fabricate the positively charged Janus particles, because this is a slightly different process. So while for the negative bits, we need to make an incubation time for 20 minutes in the silver trichloride, the formation of the positively charged Janus particles requires a longer incubation for longer than 6 hours. So you should imagine that if you have a student that forget about their experiments, and then one day they, so later on they come, they found out that they synthesized something new, which is sometimes also good. And as a result, we achieve the positively charged bits, where apart from silver chloride phase, there is a deposition of iron oxyhydroxide phase as a crystals, so small nanocrystals in the form of rods about 20 nanometer each. And this oxyhydroxide are also known to be as a co-catalyst in the visible range. So basically, the zeta potential of such bits shown to be plus 26 milliwatt. This is very nice. And then if you really think now about the proposed mechanism of motion of the positively Janus particles under green and blue light, sorry, forget about green and blue, this will come later. We see that generally speaking, the iron oxyhydroxide generally helps to support the decomposition of the silver chloride, either via transferring of the hot electrons to the silver cluster or by direct transfer of the electrons into silver chloride. But the result is so that such particles, positively charged particles, moving towards the cap. It's in contrast to the negatively charged bits. And if you also make a small comparison between their motion in the blue and the green light, we see that the negative bits, they are all, in principle, almost do not move on the green light, and they have a certain motion, good motion, and in the blue light illumination. But the positively charged particles that generally reveal much higher velocity than the negatively charged bits. They also reveal dependence in green, being illuminated by green, and also they act as we think that we attribute it to the fact that there is an acting additional co-catalyst, which is actually the iron oxyhydroxide that helps to intensify the motion of the bits. Also, please note that these two particles, they also look a little bit different. You see, the negatively charged bits, they have a large nano clusters at the cap, while the positively charged bits are completely covered with this tiny iron containing catalyst. So, and now we go to the next part, and we try to explore what happens when the Janus particles are interacting with the charged wall. So particles are charged, so more interesting would be to study the motion of both, at the first negatively and then the positively charged bits. Generally, very, very briefly, what we notice, our knowledge before, is that, okay, negatively charged bits move away from the cap, positive bits move towards the cap, mostly like this. Also, please note that we very frequently observe that the negative particle like to move away from the surface. This may be quite important information for the future. So what do we want to explore? We want to interact, to explore how such bits will interact with electrical charges at the surface. So in order to address these questions, we need to, probably we can try to using the approach by combining the self-electrophoresis and electroosmotic flows, which bring us to Helmholtz-Malachowski equation, which was proposed also several years ago, that gives us the dependence between the velocity of the object, the electric field, which is generated near the cap due to the presence of a concentration of the ions there. And the interesting term here is that there is a dependence, there is a dependence on the difference from the zeta potential of the particle and the wall. And that means that generally speaking, this velocity on the zeta potential difference should be somehow linear. And we're quite curious to explore these interactions further. So let's now look first of all at the surface. First of all, if we start to really study the phenomena at the negatively charged surface, we should say that positive bits will stuck to it. This is why we, in the future, at the negative surface, we investigate only the negatively charged particles, and the same is for the positive wall. So if we look first at so now the important challenge is to provide the negative and positive charges at the surface, and this was done by means of a surface functionalization. We have a certain experience in that, and in order to create a negative charge at the surface, we use a different kind of silane molecules. Here, there is starting from the glass that also gives a pretty strong negative zeta potential at the surface, using APTS, also succinic anhydride, MPTS, and so on. And for the formation of the positive charge, we use another silane that have an amino group at the surface, and that helps to form the positive charge. So if you try to look at the negatively charged surface and try to see what are the characteristic motion at this different substrates. And in this case, we see that many particles, again, try to move away very frequently from the substrate, but we also do not see very strong dependence on their motion, which is also somehow strange. On one hand, so if you look now a summary of the different molecules that we were immobilizing at the surface of the glass, and we try to measure also their potential of the surface, we see that generally we have a pretty broad range of surface charges from around like less than 20, like 15, up to 60 millivolt. And we see that still also there is a very broad change of zeta potential. We do not see any coupling basically to the surface. And this we just discuss a little bit later. But if you look at the positively charged surface, we see completely different behavior. So I must admit that we only use the APTS solution. We just change the concentration of the amino groups at the surface. And please look what is happening in this particular case. If you have a short, like very low amount of molecules at the surface, we have a slow motion. But if the concentration of the amino groups at the surface increases, the motion of particle increases also very much. That confirms more or less our initial idea. When we try to measure the velocity versus the functionalization time, we see that it increases with a certain leveling off at the later time scale that could be related to a saturation of the binding centers at the surface. If you also add here the values of the zeta potential, we see that they are more or less in a correspondence. And as a summary, we just say here is that we investigated, let's say, all this possible combination for the negative and positive charged particles. And we see that the negatively charged particles at the negative charge walls doesn't show us a good coupling to the surface, mostly due to the fact that most probably the particles are moving away because of the fact that their caps are always more turned during their motion, are more turned to the surface, that potentially lead to some anti-gravitatic effects in this case, and they're moving away, therefore they have a low coupling to the surface. While in the case of the positively charged Janus particles, we observe the opposite tendency, that particles always tends to move near the surface. This is why the surface charge can be, charge of a surface can be really well explained. So this gives us a very important information of what is happening at the surface. And now the next question appears: if we try to make this environment a little bit more complex and try to pattern it, basically to combine both together the positive and negative charged surfaces and to place the particle there to see what will happen. I know that there were several, this question is already was already interesting to many people in the community, and I've seen already several theoretical papers about that, also from a group in Stuttgart. And we are trying also to address it experimentally now. So how would Janus beads behave? Here, I must admit that we immediately use the positively charged beads because they tend to stay near the surface and not flying away. And there are like possible configurations that we can use here in this way. So how do we fabricate the positively and negatively charged surface? We perform the methods of the photolithography, and in this particular case, I just should admit that we use a very thin film of a gold, around 5 nanometer, that will provide us a negative charge, while the positive charge will still be provided by APTS layer due to the amino groups. So that means that the white substrate is always plus, dark substrate is always minus. Please also pay attention that the pattern is mechanically flat for the particles. It's around 5 nanometers. The roughness of a microscope glass is also 3-5 nanometers. So we are staying within this roughness sizes at all completely. At the same time, if you estimate the distance, separation distance between the particle typically and the substrate, it may reach several hundred nanometers. That means that 5 nanometer gold does not play a role here at all. So let's now turn our eyes to what is happening when the particle is coming to the interface. This is very interesting. We found out that mostly in the 90% of the cases, positively charged Janus particles are getting reflected from the plus-minus interface. And that when sometimes the particle is flying onto the negatively charged area, there are two scenarios. 90% they get stuck. Sometimes when they're flowing on it, the particles are lifted to a third dimension, so they're not staying close to the surface. Second interesting investigation that we found out is the angle of reflectance, in this case, is almost always larger than an incident angle. It's like a little bit of dissipation of the energy in this case. And another important thing is also to mention is that, again, that particles do not feel the mechanical barrier. And the question is, what the barrier do they feel then? So in this case, we're still considering this problem. We try to make a geometry, understand very well the geometry of the system and what is happening. But of course, we try to solve the problem within the soft electrostatic barriers. And let's see whether things will also work well. But the fact that angle of reflectance is always larger tells us that the multiform reflection may lead to rectification and alignment of the particles in more complex structures, what we also see later on when we try to test their motion in the different patterns. So we see that in the straight channel, when the channel is pretty large, the particle mostly feel only one wall and it's already getting aligned along the wall. If it place them in a more complex dot-like environment, particle is always reflected, getting reflected and moving between the negatively charged dots. In a more complex circular pattern, it moves mostly along the circle. In the ring-like geometry, the same. Here is even very interesting phenomenon because we can observe here multiple reflections from the walls. So we are working further on understanding this pattern, and the important task is not only to understand, but also to see if we can do something useful with that, go from motion to function. And we're also trying to make kind of a particle focusing geometry that can help us to transport some small objects through the narrow constrictions. And in this point, I would like now also to switch to the last part of my presentation, and to speak now about the interaction with the passive matrix, because apart from the walls and potentials, there are maybe also another participant in the system. And in the future, we represent these participants, we model, let's say, possible cells or microbes or so, just with the presence of the passive beads. And in all our further experiments, we're speaking about polystyrene particles, also of a 2 micrometer in diameter, that surround the micromotors. Also, we should mention that these experiments we all done with the negatively charged particles, not the positive as in that case, but the negatively charged particles. So one of the interesting first works that we have done on the interaction with the matrix of the crowded matrix is trying to investigate the effect of Janus particle assemblies on the repulsive phenomena here. We found out is that if we have a mixture of active particles and passive particles here, shining the light on it will lead to so-called exclusion phenomena of the passive and active, between the passive and active, meaning there is a strong repulsion of the passive particles that are negatively charged from the active center. So if you also look at the more or less on dynamics of this, we see that actually the longer we wait, the longer particle, the further away the passive particles are moving. And there are also some preliminary analysis that we just wanted to share that depending on the size of the cluster, there is always a preference whether the cluster is moving away from the passive particles or other way around, the passive particles are moving very efficiently way. So if you have just a very small cluster, the passive matrix is not affected, but actually the cluster is moving away. So, but this was just a really initial work on that. But a much more interesting phenomena are observed here if we try to study the really crowded environment. And I was inspired here actually by work of Lucio Isa and their work when they were trying to shoot the laser. There is a small Janus particle inside covered by gold, and they're shooting laser on the sample. And because of plasmonic heating of the system, they could generate kind of thermal shock, let's say, that is distributed into the dense environment around, which basically can help us to consider the model for the stress propagation and the macroscopic granular and crystalline matter. So we were quite interested also to see what can we do with applying the active motors in the dense environment, And here, very interesting phenomena here is just to take into account is that apart from the exclusion phenomena that was already demonstrated for non-dense medium, there might be also influence of the asymmetry of the Janus particle and the fact that the reactants and the reaction products are distributed very much unequally around it. And all this is possible to observe is only in a dense system. It's not possible to see if you have only several passive bits around. So when we try to look at the anisotropy really, we see that we have to consider the situation where the Janus particle is fixed to the substrate and is surrounded by multiple passive bits in the environment. So when the light is shining, we see that there is a formation of an the distribution of the ions around it that leads to the repulsion of the long-range repulsion of the surrounding matrix. As the reaction is getting weaker with the time, the particles start to be back, slowly be back and coming back to their old positions. We also, of course, perform this analysis over the time and also in the circular diagrams to see actually to quantify actually the distances of the interaction between the Janus and between the passive. The more interesting situation appears if the particle is fixed to the surface but is rotating. And then we also can see how the matrix can adapt to the environment upon particles rotation. This also help us to, I think I forgot to add one graph, but what I just wanted to say is that once performing the quantitative analysis of such a system, one can also try to quantify the rotation of such bits just by analysis of the surrounding matrix. This can also help to analyze the rotational diffusion of such particles also that is affected by the matrix. And we also have the results that are represented in our recent article, but unfortunately, I think I forgot to add it. This is pity. Probably it will appear a little bit later on, I don't know. Okay, but apart from the fact that the particle can rotate and the particle has, because of the nature of anisotropic nature of Janus particles, we also have the anisotropic exclusion phenomena. The exclusion phenomena by itself leads to compactization of the passive colloidal matrix around. If you can look here, there is a snapshot showing from the time 0 when the light is off to say 5 seconds when the exclusion area around the Janus particle is maximum. We also tracked all the particles around, these are around 200 bits over the time to observe what is happening around the particle, how compact the medium becomes, and how far this effect is prolonged. And this also helps us to, we could also do this with the radial distribution function and also nearest neighbor distributions here in the around the bits. We also see that shining the light and exclusion leads to indeed to compactization of the medium, to closer nearest neighbor distribution between the bits, which is shown by a blue curve, and also by and the same is also observed in the radial distribution function. But of course, compactization means that the medium becomes a little bit more dense, but still, at the moment, that is only the conclusion there. We also can try to investigate what is the spatial distribution in this compression, how far this compression goes far, yeah? And by analyzing, sorry, there is a cut off here, they're analyzing the MSD as a function of distance from the Janus particles. We see that the increase of the particle motion is observed only to the certain critical distance, which is around 20 micrometer, basically 10 particle diameters, where such defect that is introduced into the passive matrix can do. So basically one defect can affect the environment up to 10 particle distances, more or less. But what we were speaking about the compactization, we see that there is a decrease of the interparticle distance, but that case was not extreme. What happens if the density of the matrix is pretty high, and we have what is happening in this case? Yeah, so it means that if we have a certain number of the Janus particle defects, we can come to some levels of the packing fraction that are already close to, let's say, critical for the phase transition. And we were very curious, can we, by increasing the amount of the defects, lead to the, actually turn the phase transition in this situation? And we increased the density of the Janus particles here around, and we see that by shining the light, the exclusion phenomena lead in this case to the quasi-crystallization and the phase transition in the colloidal matrix. This was very interesting. We performed a lot of quantitative analysis in this case for a low amount of defects and a high amount of defects, and performed studies like the quantitative study by means of the Voronoi diagram, where we see that with a high amount of defects, we can really get very good, very large phases with the hexagonal packing that is shown by hexagons with in a yellow color. And the interesting thing is also we performed the modeling with the help of, it was done not by me, by Vyacheslav Misko, is our collaborator from Belgium. And interesting here was the following, that if we have a complex matrix, if you have a fluid state of the colloidal system, so typically what we expect is that if we add defects, the defects should kill the order in the system. But in this particular situation, we are adding more defects into the system, and introducing of the defects leads to crystallization of the colloidal crystal. So this also reminded us of one of the very old, relatively old paper about so-called freezing by heating, where there is a citation here. The one interesting feature of this transition is that the crystallized state with a higher total energy is obtained from a fluid state by increasing the amount of fluctuation. So this is a little bit a counterintuitive phenomena, but it's true that the compression in this particular situation and the amount of defects can lead to increased to the local phase transition in the system. So at this case, I would like to summarize and just very briefly saying that I hope I could describe how the light-driven Janus streamers, what we do with this, how we try to understand them and to understand different aspects of their microenvironment. We tune their physical-chemical properties, try to understand their interaction with the active and passive players, and also with the channels. And what is our future directions after we understand the streamers itself? Important, of course, is to see, can we try also to do some really useful things going, let's call it really from motion to function. So we are designing the very interesting fluidic geometries at the moment in the complex pattern to demonstrate the guidance of the particles and to make something like a focusing, sorting, and so on. On the other hand, if we imagine the Janus motors ever on the microfluidic chip, how should we always control them? What they do. We cannot simply let them without control. We should always keep this in mind. At the moment, people use the microscopy to follow them, but if we speak about a miniaturized system, do we always want to use the microscopy to use them? So therefore, there should be some feedback control here. And the feedback control typically is realized, for example, with the electronic components. And here we also try to implement our other expertise in the group is small nanoscopic sensors where the sensing area are extremely small here, and the sensing is done by means of the nanostructures as well, and whether the sensors could be integrated in different areas of the chip to perform and to detect the passage of the bits earlier or later. So these are more larger visions where we would like to go. And at this stage, I would like also to thank to all our group, and also to thank to all our fundings and support, and also to thank you for your attention. And sorry if it's a little bit too long, I don't know. So thank you very much.
Thank you, Larysa, for this nice, interesting talk. Now we have a time for discussions. Please, if people have questions, go ahead and ask Larysa. Okay. So maybe I start with my question. So in your in the case of charged Janus particles, it's true that those metallic nanoclusters, they sit on the polystyrene side, and the silver clusters, they stay there, and then you have effectively the electric dipole plus minus charge, or no?
Let me now turn to the positive particles itself. Okay, this was the slide, I think. So we observed, I did not show all our results here, of course, because UCI anyways was almost too late. So what we observed is that if you have a positively charged Janus particle that is also covered by iron oxyhydroxide, we made the SEM analysis, made the focused ion beam cuts also to see what's happening in the cap. And our conclusion is the following: the iron oxyhydroxide covers all the surface, but still there are components. There are silver and silver chloride in the cap. For this, we also did this energy dispersive X-ray, and that helps us to see the elemental distribution of the elemental distribution around the particle. And we see iron everywhere, not in very high fraction. It looks like it's a lot, but in fact, compared to the silver and silver chloride, it's not so much. And we still have a lot of silver and the chlorine in the cap. So they all coexist here, and this makes the system more complex, I would say. This is why we consider different ways of how the reaction can happen here. So how the motion can be generated. What we see that for the positive particles, they move much faster. It means that there is something else that supports this this reaction. And that's why one of them could be that there is an electrons transfer via silver clusters, but because the iron oxyhydroxide is everywhere, we should not exclude that there is also direct transfer. And this direct transfer probably more preferable in green light, where maybe because you know the plasmons, they are very active to a certain, they are active in a certain wavelength range, and they absorb very selectively. So in green, the plasmons may be not as active. This is why we have another mechanism of direct transfer, maybe.
Okay. So it could happen that your particle have a net charge, but also some small dipole moment.
You mean, so here, you know, what is interesting? Interesting here that if you compare plus and minus, so this particle, I would say, have definitely a dipole moment, negatively charged Janus particles. Why? Because the polystyrene typically is rather negatively charged, while the cap have a little bit lower electronegativity. They are not positive, but their charge is a little bit low. So they might have a small dipole moment. I think that this could be also the reason that when the, let's say, more positive and less, let's say, more negative and less negative sides interact with a negatively charged surface, maybe this is why they prefer this orientation upwards from a surface. If you think about positive, because this iron oxide is covering the particle everywhere, maybe maybe they are not. Maybe this dipolar moment is a bit smaller. This you mean this, right?
Yes. Yes. Okay. Thank you. So, are there any further questions from audience?
Can I ask one, Mikko?
Yes, Paolo, please.
Larysa, you described the role of charges, and it seems to be key to the behaviors you've observed. But this just thinking in terms of possible modeling. Everything's in solution here, right? So your charge, your Coulomb interactions are all, and your dipole interactions, if they're there at all, they're all screened, right?
We work in the ionized water, which means that so the complete screening is happening if you have a solution with which contains a lot of ions.
Right.
If you're working in the deionized water, well, we consider, okay, so there is a certain screening from the ions in solution. So we have a double layers, yes. But I cannot say that it's completely screened. They're completely screened because otherwise the particles would get stuck to the surface.
Okay. Okay, thank you.
But yes, of course, they are always in a solution.
Are there more questions from audience? I have maybe one last question from my side. So I was surprised that positively charged particles, after let's say 6 hours of exposure, they are very highly positively charged. They move so fast and so straight on your chips. There's almost no reorientation. Is it? If you observe in larger change of the orientation of motion, or they're moving always straight?
This is very good question. For all these experiments, here I showed a video for the negative charge, which was not straight, you probably observed, and then for positive, that was straight. So generally speaking, for negative charge, I used the old video that we prepared for the article, and then we made all new analysis for the positive charge. So what is the hint? So we added here the magnetic films underneath to be sure that they will move straight. This will help us to be more precise in quantifying the velocity. We found out that the trajectory that we were shown, like here, it's also a little bit older graphs. So for right now, we already have for negative charge and for positive charge particle both straight trajectories. But at the beginning, you can see that they, there are nanocluster-based surface, and some of the clusters can be more active, some of them can be less active. So that would lead to a lot of, either to a lot of fluctuations or to more active one side of the cabeçon that could lead to some torque, and that many particles could show such a spiral-like behavior. And you will agree probably that it's very hard to it will be very noisy data if you try to get the velocity out of it, because particle all the time turns.
Okay.
And this is why, in order to be more precise in this, we added the magnetic layer, again, our favorite cobalt platinum, because it gives us a very, we know where should we, how should we magnetize them to move, and to get a straight trajectory. This is why here, sorry, it's a lot of, this is why here, we have them all straight and all moving in a certain direction. I did not focus on this specifically because use of magnetic particle was just a tool to have a better analysis, but not to, yeah, it's not like some novelty or something. It was just to help us. But yes, this here we use the magnetic field to direct the motion. So it's not directly the positive charge at the surface that rectifies it.
Mm-hmm.
But what the charge is doing, the density of a charge is doing is helps to accelerate them. So if you have only a little bit, like a weak charge of the at the surface, we have a pretty slow motion. But if we have more and more molecules positively charged, more charge at the surface, we have them moving faster and faster.
Yes.
This is what we observe also in terms of velocity. But of course, the surface itself does not affect the direction. Direction affects this combination of the potential, as you could see already.
Yes. Thank you, Lucy. I understand. So are there more audience comments? No? No more further questions. So then I would like to thank Larysa for your nice talk and thank for everyone to attending it. And then we will meet next year for our next seminar. Thank you, Larysa. Have a nice day and bye-bye.
Thank you. Thank you. Yeah, I just stop sharing the screen. I stop it. Okay. Nicole, I also wanted to ask you, you were also involved in this research on the pattern, like positive negative interfaces on node.
Yes.
You left already. You were, okay. And I just wanted also to see whether you expected the case that the particle would be reflecting, or they're supposed to be. So what would be your expectations?
Yes, we have reflection. Although in our model we have no charges, it's just pure chemistry, it's just passive, neutral, diffusive phoresis, but we observe reflecting from as well. Yes, there are some parameters. There are some parameters which predict reflection. Yes, but it's slightly different than your case. It's pure hydrodynamics and neutral solutes.
So basically, if we would try to think, if I would try to ask myself, what should I do to, for example, immobilize them at the, so to make such a condition that particle basically get aligned along the interface. I'm just trying to think, what should I maybe do if I want to do this? Yeah.
Okay.
Align them.
We have predicted alignment, but it's hard to say because our system is a little bit different. I must have a look to see how charges will modify that. But you can align them.
Yeah, because it would be really very interesting, you know. In our case, let's say experimentally, it's not always easy to fine-tune each parameter. For example, maybe you see that the gold film that we have, it has minus 40 millivolt as at the potential, while the APTS at this pH value that we use is around 20, 30, so it's not symmetric. So there is no symmetry, let's say minus 40 plus 40 or minus 20 plus 20. So I'm just thinking if one should try really maybe to tune the asymmetry.
I can have a look into our paper and try to send you some hints in which range of parameters, just probably genetic phenomena, in which range of parameters you should look to get this alignment. Okay.
Yeah. Yeah. Thank you. That's really very interesting.
Okay, so thank you again for your talk. I will be in touch with you. Okay.
Thank you very much. It would be really great, and I also hope somehow to see you in Dresden. And the next year, well, after Corona, because it's now very dangerous to come here. And, yeah. And but as I say, next year, let's say maybe in the summer or something, we'll also organize the seminars. That would be great also to see you and Paulo.
Hope it will stop this pandemic and we can travel. Okay.
Okay. Thanks very much, Larysa. Bye bye then.
Thank
bye
you.
bye.
Happy Christmas. Happy New Year.
The same to all of you. Thank you very much.
All right. Okay, Miko, let's leave.
Yes, we will stay. I will have some meeting with Krzysztof and Margarida. Bye bye, Paul.
Okay, bye.